Welcome to our journey into the deep dark ocean. Find a comfortable position in your quiet resting room. Allow your breathing to become very slow and steady. Release the tension from your tired shoulders and neck. The long day is finally over and rest awaits. Close your eyes and leave the bright surface behind. We are traveling far away from the bustling world. Tonight we explore a hidden realm of quiet shadows. Let the gentle waves carry your busy thoughts away. You are safe in this peaceful dark nighttime atmosphere. Our destination lies in the remote western Pacific Ocean. This vast body of water holds many ancient secrets. We travel eastward from the distant green Philippine Islands. The surface waters here are warm and seemingly calm. Beneath these gentle waves lies a profound geological wonder. We are approaching the legendary Mariana Trench location tonight. This massive curved scar stretches across the ocean floor. It measures over 2,500 kilometers long. The trench averages almost exactly 70 kilometers in width. We navigate to the precise coordinates of our dive. Our vessel holds at 11 degrees 20 minutes north. The longitude reads exactly 140 degrees east. These exact coordinates mark the deepest region on Earth. The surface ocean reflects the pale bright moonlight above. There is no dry land visible in any direction. We are floating above a massive tectonic plate boundary. The ocean floor below is slowly shifting and changing. Geological forces work silently over millions of long years. We prepare to descend into the cold dark waters. The submersible hatches are sealed tight for the journey. Two colossal tectonic plates meet directly beneath our vessel. The massive Pacific Plate is moving steadily westward today. It collides with the much smaller Mariana Plate here. This geological intersection creates a violent deep subduction zone. The older Pacific Plate is very dense and heavy. It dives relentlessly beneath the lighter rocky Mariana Plate. This downward motion pulls the ocean floor with it. A deep valley forms along this massive collision line. The rock grinds together deep within the planetary crust. This friction generates immense heat and intense seismic activity. Our submersible begins its slow descent into the blue. The water temperature drops as we leave the surface. Sunlight quickly fades as we sink deeper down today. At 200 meters the twilight zone slowly begins. Only faint blue light pierces this cold oceanic layer. We continue sinking past the 1,000-meter mark. The last photons of sunlight vanish completely from view. We now enter the true midnight zone of water. Eternal darkness surrounds our small titanium pressure sphere completely. Our exterior lights illuminate the falling white marine snow. The descent is peaceful and perfectly silent inside here. We pass 3,000 meters without any sudden changes. The water outside is now near freezing cold temperatures. We enter the abyssal zone at 4,000 meters. Most global ocean floor regions lie at this depth. But our journey takes us much further down tonight. The trench walls begin to appear in our headlights. These massive cliffs are composed of ancient basalt rock. They guide us downward into the mysterious Hadal Zone. This zone is named after the dark underworld mythology. We cross the 6,000-meter depth threshold smoothly. The pressure outside is becoming truly difficult to comprehend. Water is heavy and it stacks up miles high. Every 10 meters adds another full atmosphere of pressure. We sink past 8,000 meters in absolute silence. The trench narrows as we approach the final depths. Our altimeter pings the approaching seafloor far below us. We finally touch down at 10,900. A soft cloud of pale sediment billows around us. We have reached the bottom of the Challenger Deep. The physical pressure at this depth is truly staggering. It measures over 1,080 standard atmospheres. This equals 15,000 pounds per square inch exactly. Imagine the massive weight of 50 jumbo jets pressing. Our spherical titanium hull easily withstands this crushing force. The water density here is increased by 5%. Even molecules are compressed tightly together in this environment. No human could survive outside this protective metal shell. Yet the cabin inside remains comfortable and perfectly safe. You can relax entirely as we explore this frontier. The surrounding seafloor terrain is alien and beautifully desolate. A thick layer of fine yellowish mud covers everything. This pelagic clay is made of microscopic biological remains. Crushed shells of ancient plankton form this soft carpet. It has been accumulating here for millions of years. The terrain is not perfectly flat as one expects. Gentle mounds and shallow depressions pattern the ocean floor. Steep rocky outcrops pierce through the thick sedimentary blanket. These jagged formations are fragmented pieces of oceanic crust. They were shattered by the immense tectonic forces above. The eternal darkness outside is absolute and completely unbroken. Our powerful halogen lamps cut through the black water. The beam illuminates only a few dozen meters ahead. Beyond that light lies an endless void of water. The water temperature is roughly 1 degree Celsius now. It is kept from freezing by the immense pressure. Currents at the bottom of the trench move sluggishly. They bring vital oxygen down from the distant surface. This slow circulation sustains life in the deepest depths. The quiet stillness of this place is deeply comforting. Few humans have ever witnessed this secluded underwater landscape. Swiss engineer Jacques Piccard first visited here long ago. He piloted the bathyscaphe Trieste with American Don Walsh. They sat in a tiny steel sphere for hours. Their brave journey proved the deepest ocean was reachable. Decades later, filmmaker James Cameron returned to this spot. He piloted the deep-sea Challenger down to the bottom. Explorer Victor Vescovo arrived later in the limiting factor. These pioneers mapped a world previously hidden from humanity. Their precise instruments revealed the true depth of darkness. We slowly lift off from the soft clay bottom. Our thrusters hum quietly, gliding over the soft seafloor. We are searching for a very specific geological feature. The Mariana Trench holds more than just crushing depths. It is home to the deepest known hydrothermal vents. These underwater hot springs are incredibly rare and mysterious. They form where seawater seeps into the fractured crust. The water travels deep into the hot mantle rock. Geothermal heat warms the fluid to extreme boiling temperatures. The superheated water then shoots back toward the surface. We navigate toward a fracture zone on the plate. Our sonar detects a massive structure looming in darkness. The water temperature sensors register a sudden slight increase. We are approaching a field of active hydrothermal chimneys. These mineral towers rise like tall skyscrapers from mud. Some reach over 30 meters tall in the water. They are located at an astonishing depth of pressure. No other hydrothermal system exists this deep underwater today. We maneuver carefully to avoid striking the fragile rocks. The submersible hovers gently near the tall chimney base. Thick black smoke appears to billow from the peaks. This is not actually smoke from a burning fire. It is a steady stream of dark mineral fluid. The heated water dissolves metals from the deep crust. Iron and sulfur compounds saturate the rising geothermal fluid. When this hot liquid hits freezing water, minerals precipitate. They solidify instantly to form dark floating particulate clouds. These particles eventually settle to build the chimney structures. This continuous geological process builds massive towers over time. We watch the dark plumes rise into the blackness. The fluid exiting these vents reaches highly extreme temperatures. Thermometers record values exceeding 350 degrees Celsius. Under normal surface conditions, this water would instantly boil. However, the crushing deep ocean pressure prevents any boiling. The water remains completely liquid despite the incredible heat. This creates a fascinating boundary of extreme thermal energy. Just centimeters away from the vent, the water freezes. This sharp thermal gradient creates strange optical shimmering effects. The halogen lights distort as they pass through heat. It looks like a visual mirage on a highway. Japanese scientists discovered deep vent fields in this trench. The famous Shinkai submersible explored these dark waters previously. Researchers found the Shinkai seep field on the slope. These specific vents sit at 5,700. Other deeper vents exist further down the steep walls. Every new expedition reveals more hidden geothermal activity zones. The Mariana Trench contains many serpentine mud volcanoes too. These geological features release highly alkaline fluids underwater continuously. They offer a completely different type of deep environment. Our journey tonight focuses on the deepest temperature smokers. The chimneys are composed of complex sulfide mineral deposits. Pyrite and chalcopyrite shine brightly in our submersible lights. These structures are fragile and can collapse without warning. New chimneys grow quickly to replace the fallen towers. The constant flow of minerals paints the rocks vibrantly. Streaks of bright yellow sulfur contrast with deep black. White calcium deposits coat the cooler outer vent edges. This colorful oasis stands out against the pale seafloor. It is a beacon of geological energy in darkness. The Earth is literally venting its internal heat here. We will study these magnificent structures in greater detail soon. The resilient life forms here defy all prior scientific expectations. Entire deep ecosystems thrive without any energy from the sun. They rely entirely on the toxic chemicals flowing from below. We will observe these strange biological creatures in due time. For now, simply enjoy the quiet peace of our descent. The deep ocean embraces you safely in its calm darkness. The geological history of this deep trench is incredibly vast. Millions of years were required to shape this ocean floor. Tectonic plates will continue moving long after we are gone. The Pacific plate slowly shrinks as it dives down deep. Meanwhile, the Atlantic Ocean slowly widens on the other side. Our planet is a living and constantly changing rocky sphere. We are merely brief visitors in this ancient underwater realm. The hydrothermal vents will eventually die out and turn cold. New vents will form elsewhere along the active fault lines. This endless cycle of geological rebirth continues in the dark. You can feel the profound isolation of this deep place. There is no wind or weather to disturb the water. The surface storms cannot reach down into this silent abyss. Everything down here moves with a deliberate and slow grace. Your breathing syncs perfectly with the gentle ocean water currents. Let the immense pressure hold you in a comforting embrace. We will remain here to explore more of the darkness. Tomorrow we will look closer at the strange vent life. For tonight, simply drift away into a deep, peaceful sleep. The Mariana Trench will keep you safe until the morning. The deep ocean concealed its greatest secrets for many centuries. Human knowledge of the Mariana Trench remained mostly theoretical. Scientists understood the immense depth of this underwater canyon. They knew about the crushing pressure of the Hadal Zone. However, the specific geological features remained hidden in total darkness. Early expeditions merely scratched the surface of this abyssal world. Oceanographers suspected the existence of deep hydrothermal activity. The tectonic plates here converge with immense geological force. The Pacific Plate slides beneath the smaller Mariana Plate. This violent subduction process generates intense subterranean heat. Researchers hypothesized that this internal heat must escape somewhere. Finding these thermal vents became a major scientific objective. The deep search required advanced technology and immense patience. A significant breakthrough occurred in the year 2003. The National Oceanic and Atmospheric Administration organized a special mission. This important expedition was named the Submarine Ring of Fire. The research vessel Thomas G. Thompson served as the base. This massive ship measured nearly 274 feet. It carried state-of-the-art sonar and mapping equipment. Dr. Robert Embley served as the chief scientist on board. He brought decades of marine geology experience to the project. The team included experts from multiple international research institutions. They focused their attention on the Mariana Volcanic Arc. This specific region sits just west of the main trench axis. The scientists sought chemical anomalies in the deep water column. They deployed sensitive instruments to measure ocean temperature variations. Finding a vent in the vast ocean is incredibly difficult. It resembles searching for a single needle in a meadow. Scientists rely on chemical traces left in the deep water. Hydrothermal vents release distinct plumes of mineral-rich fluids. These plumes rise and spread horizontally along slow ocean currents. The expedition team towed a specialized sensor package underwater. This instrument array scanned for microscopic changes in water chemistry. They looked for elevated levels of methane and hydrogen sulfide. The sensors also tracked minute fluctuations in water temperature. Days passed with only normal baseline readings appearing on monitors. The crew maintained a quiet, focused vigilance in the laboratory. Finally, the chemical sensors detected a highly significant anomaly. A distinct hydrothermal plume drifted through the pitch-black water. The discovery of the plume prompted immediate further action. The team prepared the remote-operated vehicle named Jason 2. This robotic submarine could withstand immense deep-sea pressures. Technicians carefully lowered the heavy yellow vehicle into the ocean. A long fiber optic cable connected Jason 2 to the ship. This essential tether transmitted high-definition video and data instantly. The slow descent through the water column took several hours. Sunlight faded completely after the first 1,000 meters. The vehicle entered the midnight zone of the deep ocean. The dark control room on the ship grew completely silent. Scientists watched the glowing monitors with intense, quiet concentration. The altimeter indicated the approaching rugged volcanic seafloor. Jason 2 turned on its powerful external halogen lights. The robotic vehicle hovered above the rugged volcanic terrain. The depth reading showed exactly 3,200 meters. The cameras revealed a landscape of strange geological formations. Suddenly, thick plumes of dark smoke appeared on the screens. The vehicle located a vent field near 13 degrees north latitude. Scientists named this newly discovered area the Alice Springs Field. Towering chimneys of sulfide minerals rose from the ocean floor. Some of these structures reached impressive heights of 30 meters. Dark, superheated fluid billowed violently from the chimney tops. The surrounding water shimmered due to intense heat distortion. The temperature probe recorded a reading of 300 degrees. This extreme heat existed right next to freezing ocean water. The discovery of Alice Springs was a monumental scientific achievement. However, scientists knew even deeper vents must exist nearby. The Mariana Trench offered extreme depths for potential hydrothermal activity. In 2004, a new expedition returned to the area. This time, the Japanese research agency JAMSTEC joined the effort. They brought the research vessel Yokosuka to the Mariana region. This ship carried the famous deep submergence vehicle Shinkai 6500. This manned submersible could carry a pilot and 2 scientists. It represented the pinnacle of deep ocean exploration technology. Dr. Yoshihiro Fujiwara led the biological research for this mission. The team aimed to explore the deeper sections of the trench. They wanted to find vents at unprecedented crushing depths. The heavy submersible detached from the Yokosuka at dawn. It began a long, incredibly slow descent into the trench. The thick titanium hull protected the crew from lethal pressure. Outside the small acrylic viewport, the water turned pitch black. The descent rate averaged about 45 meters per minute. It took over 2 hours to reach the target depth. The internal cabin temperature dropped as the ocean grew colder. The crew monitored their life support systems in quiet routine. The digital depth gauge crossed the 5,000-meter mark. The ambient pressure outside reached 500 complete atmospheres. This equals over 7,000 pounds per square inch. The submersible finally approached the bottom of the Sirena Deep. The Shinkai 6500 activated its powerful exterior floodlights. The bright beams cut through the eternal darkness of the trench. The seafloor here consisted of fractured basalt and serpentine rock. The crew noticed a milky cloudiness in the bottom water. This visual cue indicated the presence of active hydrothermal venting. They steered the submersible toward the source of the cloudy fluid. Soon, they discovered a field of small, delicate chimneys. These structures differed from the massive black smokers found earlier. They emitted a clear, shimmering fluid into the dark ocean. The depth here measured exactly 5,600 meters. This made them the deepest active hydrothermal vent ever discovered. The crew documented the exact coordinates for future scientific reference. The scientists inside the Shinkai carefully operated the robotic arms. They needed to collect precise temperature readings from the vents. The metal probe touched the shimmering fluid escaping the crust. The temperature registered at a mild 45 degrees Celsius. These were off-axis vents, much cooler than typical black smokers. They formed through a unique geological process called serpentinization. This chemical reaction occurs when seawater meets deep mantle rocks. The reaction generates heat, dissolved hydrogen, and various organic compounds. The robotic arm collected physical samples of the venting fluid. They stored the water in specialized titanium pressure cylinders. These pressure samples would undergo rigorous chemical analysis on land. The crew also collected fragments of the surrounding mineral deposits. The submersible spent 3 quiet hours exploring the vent field. Battery power limitations eventually required them to begin the ascent. The pilot released the heavy steel descent weights into the mud. The Shinkai slowly floated upward toward the distant ocean surface. The peaceful journey back took another 2.5 hours. The scientists reviewed their video footage in the cramped cabin. They knew they had witnessed something completely unique and profound. The Yokosuka safely recovered the submersible in the late afternoon. The discovery of the deepest vents made international scientific news. It expanded human understanding of where hydrothermal systems can exist. The findings proved that vents could form at extreme depths. These deep discoveries hold profound significance for modern marine science. The extreme pressure changes the fundamental boiling point of water. At 5,000 meters, water stays liquid at higher temperatures. This phenomenon creates unique chemical environments not found anywhere else. The fluid chemistry at these extreme depths is highly unusual. The high concentration of dissolved hydrogen provides immense chemical energy. Scientists believe this deep energy could support unique microbial life. The Mariana Trench vents offer a window into early Earth. Our planet likely hosted similar environments billions of years ago. Some researchers hypothesize that primitive life originated in such vents. The chemical soup provides all necessary building blocks for biology. Exploration of the Mariana vents continued in subsequent years. In 2014, the Schmidt Ocean Institute launched an expedition. They brought the advanced research vessel Forker to the Trench region. They deployed the sophisticated remote vehicle named Sebastian. This ROV captured stunning high-definition video of the vent fields. The powerful cameras revealed intricate details of the mineral chimneys. Scientists observed the fragile layers of precipitated iron and sulfur. They mapped the vent fields using high-frequency multibeam sonar technology. This created detailed 3-dimensional models of the entire geological area. The mapping revealed a complex network of subterranean fluid channels. The deep vents were not isolated, but part of a massive system. Understanding the Mariana vents requires studying the massive tectonic forces. The Pacific Plate is incredibly old and dense in this region. It sinks rapidly into the incredibly hot mantle of the Earth. This rapid subduction causes the overlying ocean crust to stretch. The geological stretching creates deep fractures in the ocean floor. Freezing seawater seeps down into these miles-deep tectonic cracks. The water travels incredibly close to shallow subterranean magma chambers. The intense heat expands the water and drives it upward rapidly. It dissolves heavy metals and rare minerals along the upward journey. The fluid eventually erupts back into the freezing trench ocean. The sudden cooling causes the dissolved minerals to precipitate instantly. This continuous cycle builds the towering chimney structures over centuries. These deep-sea thermal springs operate in perpetual, calming silence. They are completely removed from the bright world of sunlight. No storms or surface weather ever disturb their steady flow. The mineral chimneys grow a few centimeters every single year. Some of the larger structures are thousands of years old. They stand like ancient, silent cathedrals in the oceanic abyss. The surrounding water remains near freezing at all times. The thermal contrast between the hot fluid and cold ocean is stark. The deep vents release a steady hum of geological energy. This continuous energy slowly transforms the chemistry of the entire ocean. The process is slow, methodical, and completely uninterrupted by time. The scientists who found these vents showed immense personal dedication. Dr. Patricia Fryer also contributed greatly to Mariana Trench geology. She studied the massive serpentine mud volcanoes near the vent fields. Her research connected the deep hydrothermal activity to tectonic movements. The combined efforts of these researchers mapped the previously unknown. They transformed a dark, blank space on the map into reality. The data collected by the Jason II and Shinkai remains vital. It informs current models of ocean chemistry and global heat transfer. The physical samples reside in climate-controlled geological research repositories. Students and marine researchers still study these fascinating rocks today. The legacy of those early expeditions continues to inspire marine geologists. Right now, the Mariana vents continue their quiet, steady eruptions. Deep beneath the Pacific waves, the mineral-rich hot fluid rises. The tiny mineral particles drift slowly down to the abyssal plain. The massive tectonic plates shift by imperceptible fractions of a millimeter. The crushing ocean pressure holds the entire system in perfect equilibrium. This deep hydrothermal cycle represents the slow breathing of the planet. Earth releases its internal heat through these deep ocean valves. The geological process is ancient, steady, and profoundly calming to consider. The absolute darkness of the trench embraces this continuous natural rhythm. The deepest vents remain hidden, safely protected by miles of water. They wait patiently in the dark for the next robotic visitor. Deep beneath the ocean waves lies a hidden geological engine. The Mariana Trench is born from immense tectonic forces. Here, the massive Pacific Plate meets the Mariana Plate. This slow collision shapes the deepest seafloor on our planet. The Pacific tectonic plate is older and incredibly heavy. It slowly sinks beneath the much lighter Mariana Plate. Geologists call this slow downward descent a subduction zone. This specific tectonic process began over 50 million years ago. The sinking ocean rock plunges deep into the Earth mantle. Intense heat and extreme pressure melt the descending oceanic crust. Magma slowly rises upward through deep cracks in the crust. This rising magma forms the Mariana Volcanic Island Arc. Just behind this volcanic arc lies the Mariana Back Arc Basin. The seafloor in this region is actively pulling itself apart. Tectonic spreading rates vary across this dark ocean basin. Scientists measure a spreading rate of 3 centimeters annually. This is considered a slow-spreading mid-ocean ridge environment. Slow spreading allows deep tectonic faults to penetrate the crust. Cold seawater travels down these faults into the hot rock. The ocean water reaches depths of several kilometers underground. Temperatures down in the crust can exceed 400 degrees Celsius. The surrounding ocean floor consists primarily of dark basalt. Basalt is a dense igneous rock formed from cooled lava. Further down, the oceanic crust reveals thick layers of gabbro. Below the gabbro lies the upper mantle rock called peridotite. Peridotite contains exceptionally high amounts of iron and magnesium. When deep seawater meets peridotite, a complex chemical reaction occurs. Geologists refer to this unique alteration process as serpentinization. This chemical reaction alters the peridotite into soft serpentinite rock. Serpentinization naturally releases heat and hydrogen gas into the water. This dissolved hydrogen becomes vital fuel for deep biological communities. The chemically altered fluid becomes highly buoyant and rises quickly. The ascending hydrothermal fluid dissolves minerals from the surrounding rocks. It carries heavy loads of dissolved iron, zinc, and copper. The superheated fluid shoots out of the seafloor into darkness. Ambient ocean water at this depth sits near 2 degrees Celsius. The sudden temperature drop causes dissolved minerals to precipitate instantly. Dark, billowing clouds of metal sulfides erupt into the water. These microscopic particles slowly settle to build massive chimney structures. Some of these mineral chimneys grow up to 30 meters tall. Scientists call these towering mineral structures deep ocean black smokers. Other nearby vents emit lighter fluids rich in dissolved silica. These lighter mineral emissions form delicate and fragile white smokers. The exact mineral composition varies depending on the deep host rock. In 2003, marine scientists made a stunning discovery. The remotely operated vehicle JASON explored the Mariana Back Basin. Dr. David Butterfield led the chemical analysis of the vent fluids. The research team found the Alice Springs hydrothermal vent field. This active field sits at a depth of 3,600 meters. The towering chimneys here are unusually rich in zinc and lead. Another famous geological site is the Forecast Vent Field. The research vessel Forca visited this remote site quite recently. The ROV Sebastien captured high-definition footage of the boiling vents. Forecast features actively venting chimneys made of pure solid chalcopyrite. Chalcopyrite is a beautiful and highly conductive copper-iron sulfide mineral. These deep mineral deposits contain trace amounts of gold and silver. The exact coordinates are 13 degrees and 24 minutes north latitude. The precise longitude is 143 degrees and 55 minutes east. The deepest known hydrothermal systems exist directly within the trench. The Shinkai Seep field was officially discovered in 2010. It is located at an astonishing 5,700 meters deep. The Japanese submersible Shinkai 6500 explored this incredibly dark abyss. Dr. Patricia Fryer carefully studied the unique geological formations found here. This specific site does not have traditional black smoker chimneys. Instead, it features very slow seeps of clear mineral-rich water. The fluid gently emerges from heavily fractured serpentinite rock formations. The water temperature at this seep is only slightly elevated. It measures around 13 degrees Celsius at the primary source. The geological age of these deep seep formations is quite ancient. Carbon dating suggests they are tens of thousands of years old. The Mariana Back Basin itself began forming 6 million years ago. Relentless tectonic forces slowly tore the older volcanic island arc apart. This massive continental rifting created a deep valley on the seafloor. Intense volcanic activity eventually filled the valley with fresh basaltic lava. Pillow lavas form when hot flowing magma touches freezing ocean water. These smooth, rounded rock formations cover the vast basin floor entirely. Dr. Ken Rubin analyzed the radioactive age of these specific lavas. Some volcanic flows erupted less than 100 years ago. This proves the Mariana Trench remains highly geologically active today. The Snail Vent is another truly fascinating deep hydrothermal site. It rests quietly at 2,800 meters in depth. The thick chimneys at Snail Vent are composed primarily of sphalerite. Sphalerite is a dense crystalline mineral containing both zinc and iron. The internal fluid temperature reaches 280 degrees Celsius. The crushing deep ocean pressure prevents this superheated water from boiling. At this depth, the pressure is nearly 300 atmospheres. The Pacific Plate continues to move westward at a steady pace. It travels about 40 millimeters every single year without fail. The oceanic crust bends sharply downward into the dark Mariana Trench. This severe bending creates massive fault lines parallel to the trench. Deep earthquakes frequently rattle these unstable ocean floor fault lines. Seismic waves help geologists accurately map the descending tectonic plate. The subducting slab carries seawater trapped deep within its mineral structures. As the slab sinks deeper, the surrounding pressure increases immensely. The trapped ocean water is forcefully squeezed out of the solid rock. This released water lowers the melting point of the surrounding mantle. Flux melting generates vast subterranean chambers of glowing liquid magma. This magma slowly ascends through the overlying Mariana tectonic plate. The Mariana Trough is a massive crescent-shaped back arc-spreading basin. It stretches for over 1,300 kilometers in length. The deep trough separates the active and remnant volcanic island arcs. Tectonic spreading in the central trough is highly asymmetrical and complex. The eastern side of the basin spreads faster than the western side. This uneven expansion creates a complex topography of deep ridges and valleys. Axial volcanic ridges completely dominate the center of the dark trough. These ridges resemble miniature mid-ocean tectonic spreading centers in their structure. Thin sheet flows of liquid lava spread across the flat ocean valleys. The lava cools rapidly to form smooth, glassy obsidian rock crusts. Over time, falling marine sediment slowly covers the older cooled lava flows. The sediment consists of microscopic plankton shells and fine volcanic ash. Hydrothermal circulation requires a powerful and consistent deep heat source. Shallow subsurface magma chambers provide the necessary thermal energy for venting. These magma chambers sit just 2 kilometers below the fractured seafloor. Freezing seawater infiltrates the highly porous upper oceanic basaltic crust. The water percolates downward through a complex network of microscopic microfractures. As it descends, the seawater loses all its oxygen and dissolved magnesium. The deep fluid becomes highly acidic and incredibly chemically corrosive. It aggressively leaches heavy metals from the surrounding hot basaltic rock. The hot, buoyant fluid channels into very narrow geological upflow zones. It races toward the seafloor at velocities of 1 meter per second. The open vent acts exactly like a natural geological pressure valve. The very first mineral to precipitate is usually a mineral called anhydrite. Anhydrite is a calcium sulfate mineral that forms extremely quickly underwater. It creates a fragile white framework for the growing hydrothermal chimney. Inside the thick chimney walls, fluid temperatures remain incredibly high. Shiny copper iron sulfides line the inner hot fluid conduit. The porous outer walls consist entirely of darker zinc and iron sulfides. Over several decades, the mineral chimney walls slowly thicken and harden. Eventually, the thick mineral deposits can completely block the vent opening. The highly pressurized fluid must then find a completely new pathway. It forcefully breaks through weaker rock to form fresh new chimneys. This continuous process creates a sprawling underwater forest of mineral spires. Some hydrothermal vent fields cover areas larger than professional football fields. The total mass of deposited metal sulfide is truly staggering to behold. Marine geologists estimate millions of tons of valuable ore lie resting here. In 1987, the famous deep submergence vehicle Alvin finally arrived. Scientists mapped the central Mariana Trough accurately for the very first time. Dr. Harmon Craig led this groundbreaking and historic deep-sea expedition. They discovered the famous Burke hydrothermal vent field during this dive. The Burke field is located at 3,400 meters deep. The fluid here contains unusually high levels of dissolved carbon dioxide. Liquid carbon dioxide droplets actually bubble directly from the sandy seafloor. This strange chemical phenomenon is rarely seen in other deep ocean basins. Another major mapping expedition occurred later in 2004. The Japanese research vessel Yokosuka surveyed the northern section of the trough. They successfully deployed the autonomous underwater vehicle named Urashima into the depths. Urashima used high-resolution sonar to map the incredibly rugged underwater terrain. It identified the massive Archean site hydrothermal vent field in the darkness. This unique field features towering extinct chimneys made of pure white silica. Extinct mineral chimneys no longer emit any hot hydrothermal fluids whatsoever. They slowly dissolve back into the cold, crushing deep ocean water. The crumbling mineral structures provide perfect habitats for deep-sea glass sponges. Scientists use precise radiometric dating to determine exact hydrothermal vent ages. Decaying lead and radium isotopes reveal the hidden timeline of geological activity. Active, smoking chimneys are often less than 50 years old in total. However, the underlying massive hydrothermal system is usually much older than that. Some vent fields have been continuously active for over 4,000 years. The deep subterranean heat source slowly migrates along the active spreading ridge. As the magma moves, old vents die and new thermal springs form. This endless cycle of geological birth and death shapes the entire seafloor. The oceanic crust right here is incredibly young geologically speaking. The youngest basaltic lavas exhibit a highly glassy, completely unweathered appearance. Older ocean basalts are heavily altered by centuries of slow chemical weathering. Dark manganese crusts slowly form on the exposed surfaces of older rocks. These metallic crusts accumulate at just 1 millimeter per million years. The Mariana Forearc region hosts a completely different type of geological wonder. Massive serpentine mud volcanoes slowly rise from the dark, flat ocean floor. Our journey takes us deeper into the Mariana Trench. The research vessel Fokker holds a steady position above. Remotely operated vehicle Sebastian descends through the dark water. We are approaching a highly active hydrothermal vent field. The depth gauge currently reads nearly 5,000 meters. Total darkness wraps around the titanium frame completely. Powerful halogen lights pierce the eternal midnight ocean gloom. A strange landscape slowly emerges from the muddy seafloor. Towering mineral structures rise like ancient cathedral spires here. These are the famous black smokers of the abyss. Scientists first discovered similar structures during the late 70s. Geologist Robert Ballard led that groundbreaking initial expedition. Here in the Mariana region, the chimneys grow taller. Some mineral towers reach over 30 meters in height. They cast long shadows across the desolate ocean floor. The surrounding water pressure is roughly 500 atmospheres. Thick dark plumes billow continuously from the chimney peaks. This is not actually smoke escaping from the rock. It is superheated fluid carrying heavy dissolved mineral loads. Temperatures inside the vent throat reach 400 degrees. Normally, water would instantly boil at this extreme heat. The crushing deep ocean pressure prevents any vapor formation. Instead, the fluid enters a unique supercritical physical state. It behaves simultaneously like both a liquid and gas. The internal chemistry of these black smokers is complex. Magma chambers heat seawater that seeps into crustal faults. This heated water dissolves minerals from the surrounding rocks. Iron and sulfur combine to form dark iron sulfide. Copper and zinc are also stripped from oceanic crust. The fluid becomes highly acidic during this subterranean journey. Its pH level often drops below nearly 3.0. This acidic mixture eventually shoots upward toward the seafloor. The superheated fluid eventually hits the freezing ocean water. A rapid chemical precipitation reaction occurs almost immediately. Dissolved metals solidify into tiny dark particulate matter. These particles create the illusion of thick black smoke. Over time, these falling minerals build the towering chimneys. The walls of the chimneys are incredibly porous structures. They grow at astonishing rates of several centimeters daily. This rapid growth constantly alters the local underwater topography. Not all hydrothermal vents produce these dark metallic plumes. White smokers represent another fascinating geological phenomenon here. These lighter chimneys emit a pale, milky chemical fluid. Their internal temperatures are significantly lower than black smokers. White smoker fluids typically range around 200 degrees. They lack the heavy iron sulfide concentrations found elsewhere. Instead, they carry high amounts of barium and calcium. Silica compounds also contribute to their distinct pale coloration. The Alice Springs vent field contains numerous white smokers. This specific field sits deep within the Mariana back arc. Japanese submersible Shinkai 6500 explored this area extensively. Researchers mapped the precise coordinates during early summer expeditions. They recorded fluid emissions rich in dissolved carbon dioxide. One famous site is appropriately named the Champagne Vent. Here, liquid carbon dioxide bubbles rise through the water. The bubbles resemble the effervescence of a sparkling wine. The physical structure of a white smoker is delicate. Barium sulfate forms fragile crystalline crusts along the exterior. These pale towers often collapse under their own weight. New chimneys quickly begin to form over the ruins. This cycle of destruction and rebirth continues for millennia. Dr. Patricia Fryer has studied these cycles for decades. Her research reveals the slow evolution of vent fields. Tectonic shifts constantly alter the flow of subterranean fluids. The acoustic environment near these vents is surprisingly active. Hydrophones capture the low rumble of escaping pressurized fluids. It sounds like a distant, continuous subterranean waterfall. The rushing fluid creates a mesmerizing visual distortion effect. Differences in water density cause the light to refract. This creates a shimmering halo around the vent openings. Scientists call this optical phenomenon a hydrothermal Schlieren effect. It makes the surrounding deep sea look slightly blurred. Let us examine the precise anatomy of a chimney. The outer wall consists of anhydrite and porous silica. Cold seawater continuously seeps through this outer mineral shell. The inner lining features a solid layer of chalcopyrite. This copper iron sulfide forms the primary internal conduit. A steep temperature gradient exists across the chimney wall. The interior sits at roughly 350 degrees. Just inches away, the exterior water is 2 degrees. This extreme temperature shift drives unique chemical reactions locally. Minerals constantly dissolve and reprecipitate within the porous walls. Gold and silver trace elements accumulate in these layers. Geochemists often analyze these metallic deposits with great interest. The submersible Alvin has collected numerous chimney cross-sections. These samples are brought to surface laboratories for study. Isotope analysis reveals the precise age of the structures. Some active chimneys have vented continuously for several decades. The Mariana Back-Arc Basin is spreading apart very slowly. This tectonic divergence creates deep fissures in the crust. Seawater penetrates these cracks down to the mantle boundary. The intense pressure forces the altered water back up. This process is known as hydrothermal circulation among geologists. It regulates the chemical balance of the global ocean. Millions of gallons of water cycle through these systems. The entire ocean volume passes through vents eventually. The Shinkai Seep Field offers another unique geological perspective. This area sits at a depth of nearly 6,000 meters. It holds the record for the deepest known hydrothermal activity. Temperatures here are slightly cooler than the back-arc vents. The surrounding rock is composed of ancient mantle peridotite. Water reacts with this rock through a process called serpentinization. This reaction generates significant amounts of heat and hydrogen. It does not require a shallow magma chamber below. The chimneys at the Shinkai field look quite different. They are composed primarily of brucite and carbonate minerals. Their structures are broader and less vertical than others. They resemble large, pale sponges resting on the seafloor. The fluid seeping from them is highly alkaline naturally. Its pH can reach levels as high as 12. This creates an environment vastly different from black smokers. Scientists study these sites to understand early Earth chemistry. Dr. Ken Rubin led extensive mapping of this region. His team utilized high-resolution multibeam sonar from the surface. They identified dozens of previously unknown hydrothermal vent clusters. Each cluster features a unique morphological mineral structure arrangement. Some areas contain massive sulfide mounds spanning several acres. These mounds are the remnants of ancient collapsed chimneys. They form a rich metallic pavement across the seafloor. Deep ocean currents slowly erode these dormant mineral deposits. The active vents are concentrated along narrow tectonic ridges. ROV Jason captured high-definition video of these linear formations. The footage shows steam-like fluids rising in perfect synchronization. It looks like a submerged industrial cityscape in motion. The sheer scale of the vent fields is truly immense. One particular black smoker complex is named the Urashima site. It features a central spire flanked by smaller chimneys. The main spire continuously pumps out dark, metallic fluid. Let us focus on the exact temperature measurements recorded. Thermocouple probes are carefully inserted into the vent openings. The titanium probes must withstand highly corrosive chemical environments. At the snail vent, the readout stabilized quickly today. The digital display showed 365 degrees Celsius. This precise temperature allows specific copper minerals to form. If the fluid were hotter, different metals would precipitate. This delicate thermal balance dictates the local geology entirely. The deep sea pressure here is a constant force. It compresses the venting fluids into a dense stream. This dense stream shoots upward with incredible kinetic energy. The velocity of the fluid can exceed 2 meters per second. It creates strong localized currents around the chimney base. These currents slowly sculpt the surrounding muddy ocean sediment. They form intricate ripple patterns radiating from the vent. The patterns resemble wind-blown sand dunes in a desert. Scientists continuously monitor the chemical output of these systems. Mass spectrometers analyze the fluid samples in shipboard laboratories. They measure dissolved gases like methane and hydrogen sulfide. The Mariana vents show unusually high concentrations of hydrogen. This hydrogen is a byproduct of deep crustal reactions. It provides vital chemical energy for the surrounding environment. The venting fluids also contain rare earth elements today. Neodymium and yttrium are frequently detected in the samples. The structural integrity of a black smoker is temporary. The continuous flow of acidic fluid weakens the interior. Earthquakes frequently shake the Mariana Trench tectonic plate boundaries. These seismic tremors often cause the taller chimneys to snap. A collapsed chimney immediately alters the local fluid dynamics. The pressurized water finds a new path through the rubble. A new mineral spire begins growing within several days. This rapid geological turnover keeps the landscape constantly changing. Let us observe the subtle color variations of the minerals. Freshly precipitated iron sulfide appears deep black in color. As it ages, the mineral slowly begins to oxidize. It takes on a dull, rust-like orange appearance eventually. Zinc sulfide deposits add patches of bright yellow crust. Copper compounds create vibrant streaks of deep emerald green. The robotic arms of the ROV gently illuminate these colors. Under the harsh halogen lights, the rocks look painted. The Champagne vent field deserves a closer, detailed inspection. It is located at a depth of 1,600 meters. The liquid carbon dioxide droplets here are visually fascinating. They emerge from the seafloor with a silvery sheen. The droplets are actually coated in a thin hydrate shell. This frozen shell prevents the carbon dioxide from dissolving immediately. They slowly float upward through the cold, dark water. Eventually, they transition into a gas and disappear completely. The discovery of liquid carbon dioxide vents was revolutionary. It challenged existing theories about deep ocean chemical cycles. Researchers from the NOAA Pacific Marine Environmental Laboratory contributed greatly. They deployed specialized chemical sensors to track the plumes. The sensors drift through the water column for miles. They detect microscopic changes in ocean acidity and temperature. This data helps map the invisible spread of vent fluids. The chemical footprint of a vent extends surprisingly far. We return our attention to the massive black smokers. The mineral plumes rise hundreds of meters into the water. They eventually reach a level of neutral buoyancy above. Here, the particles spread out horizontally across the ocean. This forms a massive, slowly drifting chemical cloud underwater. Oceanographers call this formation a hydrothermal vent plume layer. These layers can be detected by satellites in some regions. They play a crucial role in global marine chemistry. The base of a black smoker is equally fascinating. Massive slabs of sulfide rock form a wide foundation. These slabs are deeply fractured by tectonic stress forces. Shimmering water seeps from these cracks at lower temperatures. This diffuse flow covers a much larger surface area. It lacks the dramatic visual impact of the main chimney. However, it releases a massive volume of chemical fluid. The diffuse flow gently warms the surrounding abyssal sediment. The geological lifespan of a vent field varies greatly. Some fields remain active for tens of thousands of years. Others exhaust their subterranean heat source within a decade. The Mariana vents seem exceptionally stable and long-lasting overall. Deep mantle plumes provide a steady supply of thermal energy. The crustal rock here is heavily fractured and highly permeable. This allows massive volumes of seawater to circulate freely. The continuous fluid flow sustains the towering mineral structures. The deep ocean holds many hidden chemical secrets. We descend toward the Mariana Trench hydrothermal fields. These are among the deepest vents on Earth. The water pressure at this depth is completely crushing. Our deep submersible glides through absolute freezing darkness. We are approaching the famous Shinkai seep field. Japanese researchers discovered this site in 1992. The depth gauge reads exactly 5,700 meters. No sunlight has ever penetrated this abyssal environment. The research vessel Yokosuka launched the Shinkai submersible. Scientists inside observed shimmering water rising from the seafloor. This shimmering effect indicates a massive thermal anomaly. Superheated fluids are mixing with the freezing seawater. The ambient water temperature remains near 2 degrees Celsius. However, the vent fluids reach much higher temperatures. Some chimneys emit water exceeding 300 degrees Celsius. This extreme heat prevents the water from freezing. The crushing pressure stops the liquid from boiling. This creates a unique state of supercritical fluid. Let us examine the specific chemistry of these waters. The pH levels here reveal a harsh environment. Most ocean water maintains a slightly alkaline pH. Typical seawater averages a pH of 8.1. The Mariana vent fluids present a drastically different reality. Many black smoker chimneys release highly acidic fluids. Sensors detect pH levels dropping to 2.8. This acidity resembles the strength of pure household vinegar. Such corrosive water dissolves surrounding basaltic rocks easily. Minerals leach into the fluid during this violent process. Iron and manganese dissolve rapidly in the acidic bath. Other vent fields show completely opposite chemical signatures. The nearby Mariana Forearc contains massive serpentine mud volcanoes. These mud volcanoes release highly alkaline fluid streams. Dr. Patricia Fryer studied these structures for decades. Her team measured pH levels reaching 12.5. This extreme alkalinity easily rivals household ammonia cleaning solutions. The contrast between these neighboring sites is scientifically fascinating. No other ocean trench displays such extreme chemical diversity. Salinity measurements provide another layer of complex data. Normal seawater contains about 35 grams of salt per liter. Hydrothermal fluids here show massive variations in salinity. Deep beneath the crust, water undergoes phase separation. Intense heat splits the fluid into vapor and brine. The vapor phase rises with very low salt content. Scientists call this low salinity fluid a condensed vapor. Meanwhile, the remaining brine becomes incredibly dense and salty. This heavy brine pools in deep subsurface rock fractures. Eventually, massive tectonic shifts force the heavy brine upward. ROV Jason recorded salinity levels double that of seawater. These dense fluids flow downward along the sloping seafloor. They create underwater rivers of heavy shimmering brine. Chlorinity sensors measure these exact salt concentrations continuously. High salinity alters the refractive index of the water. This causes the visual distortion captured by submersible cameras. The high salt content also affects local mineral precipitation. Heavy metals bond with chlorides in the superheated liquid. Hydrogen sulfide is a crucial component of this ecosystem. This toxic gas defines the Mariana hydrothermal environment. Volcanic magma degassing produces massive quantities of sulfide. The concentration here dwarfs many other global vent fields. Sensors record sulfide levels exceeding 10 millimoles per kilogram. This concentration is highly lethal to most surface marine life. However, deep-sea bacteria thrive on this dissolved toxic gas. They use hydrogen sulfide for complex chemosynthetic energy production. The East Pacific rise vents typically show lower sulfide levels. Mariana fluids contain almost twice the dissolved sulfur compounds. Dr. Ken Takai analyzed these specific sulfur isotopes carefully. His research linked the sulfur to deep mantle degassing. The subducting Pacific plate carries sulfates into the mantle. Extreme pressure and heat reduce these sulfates into sulfides. The resulting fluid is rich in dissolved chemical energy. When this fluid meets cold seawater, minerals instantly precipitate. This reaction forms the towering black smoker mineral chimneys. Iron sulfides create the dark, billowing clouds of particles. Methane gas represents another vital chemical fuel source. The Mariana Trench vents emit staggering volumes of methane. This hydrocarbon gas bubbles up from deep crustal fractures. Scientists measure methane in micromoles per kilogram of water. Some Mariana vents register over 50 micromoles of methane. This is significantly higher than typical mid-ocean ridge vents. The mid-Atlantic ridge vents average much lower methane outputs. Only the Lost City field shows comparable methane saturation. However, the creation process here is entirely different. The Mariana methane originates from highly complex serpentinization reactions. Seawater reacts chemically with exposed deep mantle peridotite rocks. This hydration process produces hydrogen gas and immense heat. The hydrogen then reacts with dissolved inorganic carbon dioxide. This abiotic synthesis directly generates the abundant methane gas. Dr. William Seyfried modeled these exact thermodynamic reactions extensively. His laboratory simulations matched the actual trench fluid samples. This abiotic methane supports entire colonies of specialized microbes. These microbes form thick bacterial mats on the rocks. Comparing Mariana to the East Pacific rise is illuminating. The East Pacific rise spreads at a very rapid rate. Its hydrothermal vents are primarily driven by shallow magma. The chemistry there fluctuates rapidly over short time periods. Mariana Trench vents operate on a completely different geological mechanism. The trench is a slow-moving subduction zone environment. Fluid chemistry here remains remarkably stable over many decades. Water samples taken in 2000 match recent collections. The dissolved silica content is uniquely high in Mariana. Silica concentrations regularly exceed 20 millimoles per kilogram. This high silica promotes the growth of enormous chimneys. Some sulfide structures here reach 30 meters in height. East Pacific chimneys often collapse before reaching such sizes. The stable fluid flow allows for massive mineral accumulation. Researchers use autonomous underwater vehicle Sentry to map these. High-resolution sonar reveals forests of giant mineral spires. The chemical stability provides a reliable haven for life. The vent fluids carry heavy loads of dissolved metals. Iron concentrations are particularly extreme at these trench depths. Fluid samples show iron levels around 2 millimoles per kilogram. When the acidic fluid mixes with oxygenated seawater, reactions occur. The dissolved iron rapidly oxidizes into solid particulate matter. This creates vast plumes of rust-colored mineral fallout. Ocean currents carry these iron particles for many miles. Manganese is also highly concentrated within the vent discharge. Manganese oxidation happens much slower than iron oxidation. This creates distinct chemical gradients surrounding the vent sites. Zinc and copper precipitate closer to the chimney walls. Researchers from the Woods Hole Oceanographic Institution studied this. They deployed specialized titanium fluid samplers using ROV-JSON. Titanium prevents contamination of the highly corrosive fluid samples. Analysis revealed rare trace metals like cadmium and lead. These trace metals are toxic to most biological organisms. Yet, the local fauna has evolved specialized biological shielding. Proteins bind the heavy metals to prevent cellular damage. Carbon dioxide levels in these fluids are truly extraordinary. The crushing pressure keeps the gas completely dissolved. At 5,000 meters, gases behave like compressible liquids. The carbon dioxide concentration reaches 200 millimoles. This creates an environment rich in raw inorganic carbon. Chemosynthetic bacteria require this carbon to build organic molecules. The high pressure shifts the chemical equilibrium of seawater. It makes calcium carbonate highly soluble in the deep. Therefore, you will not find typical calcareous shells here. Organisms must use alternative minerals for their structural protection. The Mariana vents are a natural laboratory for extreme chemistry. Scientists monitor the carbon flux using deep-sea mass spectrometers. These instruments analyze the fluid composition in real time. Dr. Peter Gerguis developed some of these advanced underwater sensors. His equipment withstands pressures exceeding 8,000 pounds per square inch. The data streams continuously to the research vessel above. Let us move to the Alice Springs vent field. This specific site rests at 3,600 meters. It was discovered during a joint Japanese-American expedition. The chemical signature here differs from the deeper sites. Alice Springs emits clear fluids rather than dark smoke. The fluid temperature maxes out around 200 degrees. These cooler temperatures result from subsurface mixing processes. Cold seawater infiltrates the porous crust beneath the vents. It dilutes the rising superheated hydrothermal fluid significantly. This mixing drops the temperature and alters the chemistry. The pH at Alice Springs is slightly more neutral. It hovers around 4.5 on the scale. Hydrogen sulfide levels are correspondingly lower at this site. However, the dissolved methane concentration remains surprisingly elevated. This suggests a deep abiotic methane source remains active. The clear fluids shimmer beautifully against the dark basalt. Barium and strontium precipitate to form white mineral chimneys. These pale structures contrast sharply with the black smokers. We can compare this to the mid-Atlantic ridge environments. The TAG hydrothermal field sits in the Atlantic Ocean. TAG operates on a completely different tectonic plate boundary. Atlantic vents experience much less frequent volcanic eruption events. Their chemistry is dominated by deep fluid circulation patterns. Mariana vents are heavily influenced by the subducting slab. The Pacific Plate drags oceanic sediments into the mantle. These melting sediments add unique chemical isotopes to the magma. Helium isotope ratios reveal this deep crustal recycling process. Scientists measure the ratio of helium-3 to helium-4. Mariana fluids show a distinct subduction zone helium signature. This signature is completely absent in mid-Atlantic ridge fluids. The sediment contribution also increases the local ammonium concentrations. Ammonium provides another vital nitrogen source for deep microbes. No other vent system recycles surface sediments so efficiently. This makes the Mariana Trench a perfect closed-loop system. Another fascinating chemical zone is the snail vent site. This location is named for its dense biological communities. The chemical flow here is remarkably steady and diffuse. Instead of focused chimneys, fluid seeps through cracked rocks. This creates a broad area of warm, chemically rich water. The temperature here averages around 20 degrees Celsius. This warm bath is an oasis in the freezing trench. The diffuse flow has a unique chemical makeup. It is heavily depleted in dissolved oxygen and nitrates. The underlying microbial biosphere consumes these chemicals rapidly. What emerges is a fluid rich in metabolic byproducts. Dissolved organic carbon levels are unusually high here. This organic carbon feeds complex communities of scavenging organisms. The fluid chemistry dictates the exact distribution of life. Organisms position themselves along microscopic chemical concentration gradients. Too much sulfide is fatally toxic to the animals. Too little sulfide means starvation for their symbiotic bacteria. They must find the perfect chemical balance to survive. Gathering these chemical measurements requires incredible engineering feats. Standard oceanographic equipment would implode at these extreme depths. Engineers designed specialized isobaric gas-tight samplers for this work. These titanium cylinders maintain the crushing deep-sea pressure. When brought to the surface, the fluids remain compressed. This prevents the dissolved gases from violently boiling away. Scientists can then extract the fluids in a controlled laboratory. They use gas chromatography to analyze the volatile compounds. Mass spectrometry reveals the precise isotopic composition of metals. During a 2014 expedition, RV Forker deployed ROVs. They collected dozens of these pressurized fluid samples carefully. The chemical analysis took several years to fully complete. The results redefined our understanding of subduction zone chemistry. We learned how deeply the ocean interacts with the mantle. The Mariana Trench is a massive chemical processing plant. The dark Mariana Trench hides a secret world. Hydrothermal vents emerge from the fractured ocean floor. These towering rocky chimneys release scalding mineral fluids. Water temperatures here can reach 400 degrees. Intense pressure keeps this boiling water completely liquid. This environment seems entirely hostile to organic life. Yet a unique ecosystem thrives in this darkness. It operates completely independent of the distant sun. Solar energy never reaches these profound oceanic depths. Surface ecosystems rely entirely on the photosynthesis process. Green plants convert sunlight into usable biological energy. Down here, life requires a completely different mechanism. We call this remarkable process deep ocean chemosynthesis. Chemical energy replaces solar energy in this realm. The Earth itself provides the fuel for survival. Volcanic activity below the crust heats the seawater. This superheated water dissolves heavy metals and minerals. It rushes back up through the seabed vents. Dark plumes of hydrogen sulfide billow outward continuously. This toxic chemical becomes the foundation of life. Microscopic organisms wait near the venting fluid streams. These specialized bacteria are the true primary producers. They absorb the toxic hydrogen sulfide molecules directly. Oxygen from the surrounding seawater is also absorbed. The bacteria combine these elements in complex reactions. This chemical oxidation releases vital energy for growth. They use this energy to fix dissolved carbon. Carbon dioxide transforms into organic sugar and food. Dr. Holger Janusz first studied these unique microbes. His research revealed a hidden biosphere in darkness. Some bacteria float freely in the warm plumes. Others form thick white mats on the rocks. These bacterial mats look like fresh underwater snow. Archaea also exist in these extreme thermal gradients. They are ancient single-celled organisms with unique genetics. Some archaea consume methane gas instead of sulfide. Methanogenesis provides another pathway for deep biological energy. The Mariana Back-Arc Basin hosts many such communities. Scientists mapped these vents using the ROV JSON. They recorded coordinates at 14 degrees north latitude. The depth measured exactly 3,600 meters. The food web builds upon these microscopic producers. Tiny grazing organisms arrive to consume the bacteria. Deep-sea snails slowly scrape the microbial rock mats. The Alviniconcha snail is a fascinating local resident. Its shell appears covered in thick brown bristles. These bristles protect the snail from acidic fluids. The snail does not just eat the bacteria. It actually hosts them inside its own body. Specialized gill tissues contain millions of symbiotic microbes. The snail absorbs oxygen and sulfide for them. The bacteria produce organic carbon for the snail. This mutualistic relationship ensures survival for both species. Scientists call this process endosymbiotic chemical nutrient exchange. Dr. Nicole Dubilier extensively researched these symbiotic partnerships. Shrimp also flock to the active vent chimneys. The Coracaris shrimp swarms around the warm water. They lack functional eyes in this eternal darkness. Instead, they possess a specialized thermal sensing organ. This organ detects faint infrared radiation from vents. It prevents them from swimming into boiling water. These shrimp graze on the exterior bacterial layers. Gallet-eyed squat lobsters crawl among the venting rocks. These pale crustaceans are actually a crab species. They use long claws to sift through sediment. Their diet consists of fallen organic bacterial debris. Sometimes they actively hunt the smaller grazing shrimp. The Mariana vents host unique species of crabs. The Ostinogria crab is a dominant benthic predator. It scurries across the steep mineral chimney walls. This crab possesses a smooth and rounded carapace. It lacks ocular peduncles entirely in the dark. Sensory hairs on its legs detect water movements. Chemical sensors help it locate fresh food sources. These crabs are aggressive scavengers of the deep. They will eat dead fish or crushed snails. Sometimes they even cannibalize smaller crabs for energy. Energy flows efficiently through this compact food web. Very little organic matter goes to waste here. Every creature plays a specific ecological recycling role. The biomass density around vents is truly astonishing. It rivals the productivity of tropical coral reefs. Yet it exists miles below the ocean surface. Larger predators also patrol the hydrothermal vent periphery. Zooarcid fish slowly swim through the murky water. These eelpouts have long and slender pale bodies. They wait patiently for a shrimp to wander. A sudden strike secures their next rare meal. These fish tolerate the toxic hydrogen sulfide levels. Their blood contains specialized hemoglobin to bind oxygen. This adaptation prevents suffocation in the vent fluids. Deep-sea octopuses occasionally visit the active thermal fields. The Vulcan octopus is a rare and elusive cephalopod. It crawls over the basaltic rocks with grace. Its pale skin lacks the typical camouflaging chromatophores. There is no need for color in darkness. This octopus hunts the squat lobsters and crabs. It uses sensitive suckers to probe rock crevices. A sharp beak crushes the hard crustacean shells. The energy from the bacteria finally reaches apex predators. This entire complex web relies on geological plumbing. If the vent stops flowing, the ecosystem dies. Tectonic shifts can easily block the subterranean channels. Hydrothermal vents are highly ephemeral deep biological habitats. A single chimney might remain active for decades. Eventually, mineral deposits clog the internal fluid pathways. The scalding water stops flowing into the ocean. The vital hydrogen sulfide supply completely dries up. Without chemical fuel, the primary producing bacteria perish. The thick white mats slowly dissolve and vanish. Snails and shrimp lose their primary food source. Mobile creatures must migrate across the barren seafloor. They must find a new active vent quickly. Sessile organisms simply starve in the freezing dark. The once vibrant chimney becomes a cold tomb. Scientists observed this tragic cycle using submersible vehicles. The Shinkai submersible visited the Mariana Trench repeatedly. Researchers documented the birth and death of vents. New vents open when fresh seismic activity occurs. Larvae from vent creatures drift in ocean currents. They travel miles through the freezing abyssal plains. Most larvae never find a suitable thermal habitat. A lucky few settle near newly formed chimneys. The cycle of chemosynthetic life begins all over. We must compare this to shallow water ecosystems. A coastal kelp forest relies on constant sunlight. Seasons dictate the biological productivity of the surface. Winter brings cold water and reduced solar energy. The Mariana Vent ecosystem experiences no seasonal changes. The water temperature remains perfectly constant all year. Geological time governs this deep and silent world. We can also compare different global vent fields. The Mid-Atlantic ridge features massive towering sulfide chimneys. Those Atlantic vents host massive swarms of shrimp. Giant tube worms dominate the Pacific Ridge vents. The Rifsha pachyptila worm grows over 2 meters. However, the Mariana Trench vents possess distinct differences. Giant tube worms are completely absent from Mariana. Instead, the hairy Alviniconcha snails dominate the biomass. This geographical isolation creates unique evolutionary biological paths. The Mariana Trench acts as a deep barrier. Species cannot easily cross the vast abyssal plains. They evolve specialized traits for this specific trench. The water chemistry here also differs slightly today. Mariana back-arc vents emit fluids rich in zinc. High concentrations of dissolved iron tint the water. When iron meets cold seawater, it precipitates quickly. This creates the characteristic dark gray smoke plumes. Some vents in this region emit clear fluids. Scientists call these specific structures white smoker chimneys. White smokers release cooler water containing barium sulfate. Silica deposits form delicate pale structures around them. The research vessel Forca mapped these fields extensively. Sonar technology revealed the complex seafloor bathymetry here. Researchers deployed the Sebastian remotely operated underwater vehicle. High-definition cameras captured the alien landscape in color. They measured fluid temperatures at 300 degrees. Ambient seawater remains near a freezing 2 degrees. This extreme thermal gradient spans merely a centimeter. Organisms must navigate this dangerous boundary very carefully. Moving too close means instant death by boiling. Drifting too far brings freezing temperatures and starvation. Survival requires constant and precise physical spatial awareness. The ecosystem exists on a literal knife edge. The Shinkai Seep field lies even deeper down. It sits at 5,700 meters. Vesicomyid clams dominate this particular deep trench ecosystem. These large white clams nestle in the sediment. They also rely on symbiotic chemosynthetic internal bacteria. A muscular foot anchors them near fluid seeps. They extend siphons to draw in the sulfide. The pressure here exceeds 8,000 pounds per inch. Calcium carbonate shells normally dissolve at this depth. The clams possess a specialized thick protein layer. This periostracum protects their shells from acidic dissolution. Dr. Craig Young studied these deep benthic adaptations. His work highlighted the resilience of trench life. Every creature here represents a biological engineering marvel. Proteins are folded tightly to withstand extreme pressure. Cell membranes contain specialized lipids for structural fluidity. Enzymes operate efficiently despite the crushing deep environment. The Mariana Trench pushes life to absolute limits. Yet life does not merely survive the darkness. It flourishes in a vibrant and complex community. We slowly leave the active hydrothermal vent field. The towering smoking chimneys fade into the gloom. The dense clusters of hairy snails disappear behind. The water temperature drops back to freezing levels. The faint chemical scent of sulfur slowly dissipates. We return to the vast and empty abyssal plain. The contrast between these two zones is striking. The vent was an oasis of chaotic energy. The surrounding trench is a desert of stillness. This isolation protects the delicate chemosynthetic food web. The crushing pressure deters most human industrial exploitation. Deep-sea mining remains a distant and complex threat. For now, the ecosystem functions exactly as designed. It has operated this way for millions of years. The silent darkness preserves this ancient biological rhythm. We can only marvel at such enduring resilience. The Mariana Trench hides many more biological secrets. Our journey through this deep realm must continue. The journey into the Mariana Trench requires immense preparation. Scientific expeditions here represent the pinnacle of oceanographic research. Exploring the deepest hydrothermal vents demands extraordinary technological innovation. The crushing pressure at these depths breaks ordinary instruments. Researchers must design specialized tools for this extreme environment. In 2003, a major breakthrough occurred. Scientists aboard the research vessel Thomas Geo Thompson arrived. They navigated to the coordinates of 11 degrees north. Their longitude was 143 degrees east. This team sought the elusive deep-water hydrothermal vent systems. The remotely operated vehicle Jason descended into the abyss. It plunged to a depth of 3,000 meters. The control room remained silent during the long descent. Technicians monitored the fiber optic cables with intense focus. Deep ocean currents threatened to push the tether off course. Dr. Patricia Fryer led this groundbreaking geological expedition. Her team studied the serpentine mud volcanoes nearby. They discovered fluid seeping from the dark ocean floor. The temperature of this fluid measured 2 degrees Celsius. It was a cold seep, but it hinted at more. True hydrothermal vents in the trench sit much deeper. The Sirena Deep holds some of the deepest known vents. They exist at approximately 5,000 meters below sea level. The crushing pressure here exceeds 500 atmospheres. Standard titanium housings begin to buckle under such immense weight. Engineers developed new syntactic foam to provide necessary buoyancy. This material consists of microscopic hollow glass spheres. It resists compression even at 6,000 meters deep. The ROV Deep Discoverer utilized this advanced foam technology. It allowed precise maneuvering around the fragile vent chimneys. In 2014, another mission launched. The research vessel Okino's Explorer sailed to the trench. Scientists aim to map the Mariana Trench Marine National Monument. They used high-resolution multibeam sonar to scan the seafloor. The acoustic waves revealed towering chimney structures in the darkness. These chimneys reached heights of 30 meters above the crust. They vented dark fluids rich in iron and sulfur. The fluid temperatures exceeded 350 degrees Celsius. Surrounding seawater remained a frigid 1 degree Celsius. The thermal gradient creates a shimmering optical illusion underwater. Dr. Robert Stern analyzed the tectonic forces at play here. The Pacific Plate subducts beneath the Mariana Plate. This violent geological process fuels the deep hydrothermal activity. Magma chambers heat the percolating seawater deep within the crust. The superheated water then shoots back up through fissures. The Japanese submersible Shinkai 6500 made several dives. It explored the Shinkai seep field in the late 90s. This manned vessel carried 3 people into the profound darkness. They observed fields of white clams surrounding the vent sites. The coordinates were 12 degrees north, 144 east. Piloting a manned submersible requires absolute precision and calm. The acrylic viewport is only a few inches thick. Outside, the ocean exerts thousands of pounds per square inch. The pilots use acoustic communication to talk with the surface. The sound waves travel slowly through the dense water column. Sampling these hydrothermal fluids presents a unique engineering challenge. The superheated water boils instantly if brought to the surface. Scientists use specialized titanium syringes called isobaric gas-tight samplers. These devices maintain the abyssal pressure during the long ascent. This prevents the dissolved gases from escaping into the atmosphere. Dr. Jeffrey Seawald helped design these intricate fluid samplers. His work allowed chemists to analyze the vent fluids accurately. They found high concentrations of dissolved hydrogen and methane. These chemicals sustain the unique biological communities in the dark. The fluid chemistry varies greatly between different vent fields. The Alice Springs vent field is another crucial research site. It sits in the central Mariana Trough spreading center. The depth here is roughly 3,600 meters. The chimneys emit clear fluids rather than dark black smoke. The temperature hovers around 280 degrees Celsius. Long-term monitoring of these vents provides invaluable scientific data. Short expeditions only offer a brief glimpse of this world. Researchers deploy autonomous ocean bottom seismometers around the vents. These instruments record the microscopic earthquakes caused by moving magma. They remain on the seafloor for up to 12 months. Acoustic releases eventually free these instruments from their heavy anchors. They float slowly to the surface for data retrieval. Scientists download terabytes of seismic data to analyze tectonic shifts. This continuous monitoring reveals the life cycle of a hydrothermal vent. Chimneys can grow, collapse, and rebuild over mere decades. Temperature probes also monitor the thermal output over time. They are inserted directly into the venting fluid streams. The probes record temperature fluctuations every single minute. Some vents show stable temperatures for many consecutive years. Others fluctuate rapidly due to shifts in the crustal plumbing. The hybrid remotely operated vehicle Nereus visited the trench. It reached the Challenger Deep in 2009. While the deepest point lacks vents, the technology was vital. Nereus used a micro-thin fiber optic tether for communication. This specialized data tether was as thin as a human hair. This technological breakthrough allowed unprecedented freedom of movement underwater. Traditional heavy cables drag and restrict deep ocean vehicles. The micro-tether unspooled smoothly from the vehicle itself. It transmitted high-definition video from the deepest ocean trenches. Scientists watched the live feed from thousands of miles away. Unfortunately, Nereus was lost during a dive in 2014. The immense pressure caused a catastrophic implosion at depth. This loss highlighted the extreme risks of deep-sea exploration. The ocean remains an unforgiving environment for human engineering. Every successful dive represents a triumph of meticulous design. The Schmidt Ocean Institute launched a campaign in 2014. They utilized the research vessel Fokker for extensive trench mapping. Their remotely operated vehicle Sebastian explored several new vent sites. They discovered a unique vent field they named the Snail Site. The coordinates were 13 degrees north and 143 east. The Snail Site sits at 2,800 meters deep. It features delicate, spire-like chimneys made of barium sulfate. The fluid venting here is cooler, around 50 degrees Celsius. This temperature allows dense populations of hairy snails to thrive. The ROV captured stunning footage of this alien ecosystem. Dr. Victoria often studies the microorganisms collected from these vents. She uses advanced genomic sequencing to understand their unique metabolism. These microbes survive entirely without the energy of the sun. They consume the methane and hydrogen sulfide from the vents. Her research expands our understanding of life's absolute limits. Deploying an ROV takes several hours of careful preparation. The deck crew coordinates closely with the bridge officers. The ship must maintain its position using dynamic positioning systems. Thrusters adjust constantly to counteract surface winds and ocean currents. The ROV must descend straight down to avoid tangling. Once on the bottom, the ROV moves with deliberate slowness. The thrusters stir up fine sediment if operated too quickly. This suspended sediment can obscure the camera lenses for many hours. Pilots use robotic manipulator arms to collect geological samples. These titanium arms possess incredible strength and surprising dexterity. They carefully break off small pieces of active vent chimneys. These sulfide deposits contain valuable clues about the Earth's interior. The samples are placed into insulated bio-boxes on the vehicle. This protects the delicate minerals from the warmer surface waters. The slow ascent back to the ship takes several hours. The Mariana Trench subduction zone creates unique chemical signatures. The subducting Pacific plate releases water into the overlying mantle. This slow process lowers the melting point of the deep rocks. The resulting magma is highly enriched in volatile elements. This distinct chemistry is reflected in the hydrothermal vent fluids. Dr. Craig Moyer focuses on the microbial mats at these vents. His expeditions map the extensive iron oxidizing bacterial communities. These mats form thick, orange carpets around the cooler seeps. They thrive in water temperatures between 10 and 30 degrees Celsius. The mats can cover hundreds of square meters of seafloor. The Deep Sea Challenger expedition also contributed to trench science. James Cameron piloted the submersible to the Challenger Deep. While focused on the deepest point, the engineering advanced all deep-sea research. The submersible used specialized batteries encased in oil to resist pressure. This brilliant design prevents the battery housings from being crushed. Similar battery technology now powers long-term vent monitoring stations. These remote observatories require reliable power for years at a time. Solar power is impossible in the absolute darkness of the abyss. High-capacity lithium-ion batteries are currently the most viable solution. They power the cameras, chemical sensors, and acoustic modems. A massive international effort established the Mariana Trench Observatory. Scientists from Japan, the United States, and Europe collaborated. They deployed a network of sensors across the subduction zone. This network monitors both tectonic activity and hydrothermal fluid flow. The collected data helps predict how subduction zones behave globally. The observatory uses acoustic gliders to relay data to the surface. These autonomous underwater vehicles patrol above the vent fields. They receive acoustic signals from the seafloor instruments below. The gliders then surface to transmit the data via satellite. This eliminates the need for expensive underwater data cables. Dr. Kotsunori Fujikura led several Japanese expeditions to the trench. He specialized in the biogeography of deep-sea chemosynthetic ecosystems. His team discovered new species of provanid snails near the vents. They mapped the distribution of these snails across different depths. The findings showed how species migrate along the trench axis. The research vessel Kyre played a crucial role in these discoveries. It deployed the ROV Keiko to record depths exceeding 10,000 meters. Keiko also explored the shallower hydrothermal vent fields of the trench. It collected sediment cores from the base of the active chimneys. These deep cores reveal the historical record of vent activity. The sediment layers contain microscopic fossils of vent-dwelling organisms. By carbon dating these layers, scientists reconstruct the vent's complex history. Some vent fields in the Mariana Trough are thousands of years old. They experience cycles of intense activity followed by long dormancy. The shifting tectonic plates dictate this slow, rhythmic pulse. Measuring the exact depth of these vents requires complex mathematics. The speed of sound in water changes with temperature and pressure. Sonar depth readings must be corrected for these varying factors. Scientists use conductivity, temperature, and depth sensors called CTD rosettes. These instruments provide the necessary data to calibrate the sonar. A CTD rosette is a circular metal frame carrying many cylinders. It is lowered on a conducting cable from the research vessel. The cylinders capture water samples at specific, predetermined depths. The sensors measure the physical properties of the water column continuously. This creates a detailed profile of the ocean's layered structure. Near the hydrothermal vents, the CTD detects chemical anomalies. A sudden spike in water temperature indicates a nearby vent plume. An increase in light scattering reveals suspended mineral particles. Scientists use these anomalies to hunt for undiscovered vent fields. It is a slow, methodical search through the endless dark. We leave the isolated depths to look at the global ocean. The Mariana Trench vents differ from other hydrothermal systems worldwide. Most known black smokers exist along oceanic ridge spreading centers. The East Pacific Rise hosts vents at 2,000 meters down. The Mid-Atlantic Ridge features chimneys at similar moderate ocean depths. Our Mariana vents sit much deeper in a geological subduction zone. Depths here exceed 5,000 meters at the dark trench margins. This extreme depth creates a unique thermodynamic environment for fluids. Pressure alters the boiling point of superheated water significantly here. Fluids emerge at 360 degrees Celsius without boiling. Atlantic vents often emit fluids rich in iron and copper. The Mariana system produces highly alkaline fluids rich in hydrogen. This distinct chemistry resembles the famous Lost City hydrothermal field. However, the Lost City sits at only 800 meters deep. The Mariana Trench combines high alkalinity with crushing abyssal pressure. Scientists deployed the ROV Jason to measure these chemical differences. Sensors recorded dissolved methane concentrations much higher than typical vents. These high methane levels support entirely different microbial communities here. Researchers compare these communities to those in shallow coastal seeps. This biological divergence highlights the uniqueness of the Mariana ecosystem. This unique chemistry draws scientists studying the origin of life. Geochemist Michael Russell proposed the alkaline hydrothermal vent hypothesis. He suggested life began in warm submarine mineral springs. The Mariana vents provide a perfect modern laboratory for this. Seawater interacts with mantle rocks in a process called serpentinization. This geological reaction produces abundant hydrogen gas and mineral byproducts. Hydrogen acts as a crucial energy source for primitive microbes. Early Earth oceans were likely highly acidic and rich in iron. Alkaline vent fluids mixing with acidic seawater created electrochemical gradients. These natural proton gradients mirror the internal energy systems of cells. Modern living cells use a protein called ATP synthase for energy. This complex protein relies on a strict flow of cellular protons. Deep-sea chimneys naturally provided this proton flow for billion years ago. Minerals like greigite and makinowite formed thin walls within chimneys. These fragile iron-sulfur walls acted as the first primitive cell membranes. They safely separated the alkaline vent fluid from the acidic ocean. Microbes eventually evolved to generate their own internal proton gradients. Scientists search for the last universal common ancestor down here. This hypothetical primitive organism is commonly known by the acronym LUCA. LUCA likely thrived in a high-temperature hydrogen-rich vent environment. These deep-sea discoveries extend far beyond our own blue planet. Astrobiologists study Mariana vents to understand potential extraterrestrial life. Jupiter contains an ice-covered moon known to astronomers as Europa. Saturn hosts a small, highly active moon called Enceladus. Both moons possess vast liquid water oceans beneath thick icy crusts. Cassini spacecraft data revealed silica nanoparticles erupting from Enceladus. These particles strongly indicate active hydrothermal vents on its hidden seafloor. The Mariana Trench serves as a highly accessible analog for Enceladus. If alien life exists there, it likely resembles our trench extremophiles. NASA closely monitors deep-sea expeditions to refine their future space probes. Exploring these deep analog environments requires overcoming immense engineering hurdles. The water pressure at these vents reaches incredible destructive levels. Equipment must withstand over 7,000 pounds per square inch. Standard titanium housings begin to deform under this relentless force. Engineers use specialized syntactic foam to provide buoyancy for submersibles. This foam consists of microscopic hollow glass spheres embedded in resin. Even a tiny microscopic flaw in a sphere causes catastrophic implosion. The Japanese research vessel Yokosuka launched the Shinkai submersible. This manned vehicle successfully navigated the crushing Mariana vent fields. It required extremely thick acrylic windows to protect the vulnerable pilots. Pressure is only one of the many technological challenges faced. The vent fluids are highly corrosive to standard marine equipment. Hydrogen sulfide gas dissolves rapidly into the surrounding cold seawater. This creates localized pockets of highly acidic ocean water. Acid slowly eats away at the exposed metal of deep submersibles. Scientists must coat their instruments in specialized protective plastic polymers. Electronic tether cables face constant danger from the superheated water. If a cable touches a black smoker, it melts almost instantly. ROV pilots must navigate these jagged mineral forests with extreme caution. Communication delays through miles of fiber optic cable complicate delicate maneuvers. Power supply remains a critical limitation for deep ocean exploration. Batteries drain much faster in the freezing ambient bottom water. Temperatures outside the vent plumes hover around 2 degrees Celsius. Collecting pristine chemical samples requires complex and heavy titanium syringes. These syringes must maintain ambient pressure during the long ascent. If pressure drops, dissolved gases will violently bubble out. This ruins the precious chemical sample before it reaches the surface laboratory. The DSV Alvin was recently upgraded to handle much deeper dives. It now features advanced variable ballast systems for precise depth control. These structural upgrades allow longer observation times at the trench vents. The geological processes here create substantial deposits of rare minerals. Hydrothermal fluids carry dissolved metals from deep within the crust. When hot fluids hit cold seawater, the heavy metals precipitate out. They slowly build massive seafloor structures over thousands of years. Geologists call these formations seafloor massive sulfides or SMS deposits. These deep deposits contain high concentrations of valuable copper and zinc. They also hold significant trace amounts of precious gold and silver. The mineral density far exceeds most terrestrial mining sites today. Some nations view these deep-sea vents as future resource reserves. The global demand for rare earth elements drives this new interest. Minerals are not the only valuable resources found down here. Pharmaceutical companies show great interest in marine genetic resources. This ongoing search for biological compounds is known as marine bioprospecting. Trench microbes produce unique enzymes to survive the extreme heat. These specialized proteins remain stable at remarkably high industrial temperatures. Scientists previously isolated a famous enzyme from a shallow hydrothermal vent. The Taq polymerase enzyme revolutionized modern genetic DNA testing techniques. Researchers hope to find similar groundbreaking enzymes in the Mariana. Extremophile bacteria might hold the biochemical key to new antibiotic drugs. Deep-sea sponges often produce chemical defenses against harmful marine pathogens. This immense resource potential brings significant environmental conservation concerns. Commercial deep-sea mining poses a severe threat to these fragile ecosystems. Extracting massive sulfides requires deploying heavy destructive robotic mining tractors. These machines would crush the delicate mineral chimneys into dust. Mining operations would generate massive plumes of toxic suspended sediment. Deep ocean currents could carry these suffocating plumes for many miles. Filter-feeding organisms would quickly ingest the toxic heavy metal particles. The noise pollution from mining would disrupt deep-sea acoustic environments. Vibrations could destabilize the complex geological structures of the trench. Once destroyed, a hydrothermal vent ecosystem might never fully recover. Marine biologists classify these specific areas as vulnerable marine ecosystems. The organisms living here have evolved in complete stable isolation. They possess very slow rates of natural reproduction and growth. A single towering mineral chimney takes decades or centuries to form. If a mining tractor destroys it, the habitat vanishes instantly. Many species found at Mariana vents exist nowhere else globally. We call these highly localized organisms endemic deep-sea species. Destroying a single vent field could cause multiple species extinctions. We still know very little about these complex deep food webs. Removing one bacterial strain might collapse the entire local ecosystem. The International Seabed Authority regulates mining in international ocean waters. This global organization is commonly referred to by the acronym ISA. The ISA drafts codes to manage future deep-sea mineral exploitation. Scientists urge the ISA to implement strict environmental protection zones. They advocate for large marine protected areas around active vents. Currently, the Mariana Trench Marine National Monument offers some protection. President George Bush established this large monument in 2009. It covers nearly 100,000 square miles of ocean. The monument strictly prohibits commercial fishing and deep-sea mining activities. However, this legal protection only applies to areas within American jurisdiction. Many vent systems sit in unprotected international waters beyond borders. These vulnerable areas require global cooperation to ensure their long-term survival. Researchers deploy autonomous gliders to monitor baseline environmental conditions continuously. We must understand the natural state before any human interference occurs. Conservationists argue that the genetic resources hold more long-term value. Mining provides a temporary yield of basic raw industrial metals. Biological discoveries could provide sustainable medical advancements for future generations. The scientific community strongly pushes for a global moratorium on mining. They demand comprehensive environmental impact assessments before any commercial extraction begins. The deep sea remains our planet's last truly pristine wilderness. The Mariana Trench thermal vents connect multiple vital scientific disciplines. Geology, biology, and chemistry intersect in these crushing dark depths. These towering chimneys teach us about the violent formation of oceans. They offer a highly plausible narrative for the earliest cellular life. They guide our ongoing search for organisms on distant frozen moons. Yet human industrial ambition now threatens their quiet ancient existence. We stand at a critical crossroads for deep ocean conservation today. Technology allows us to reach these remote depths to learn today. The exact same technology gives us the terrifying power to destroy them. Our collective choices will determine the future of these abyssal sanctuaries. Let us look at the shallow coastal hydrothermal seeps. Sunlight easily penetrates the water above those coastal systems. The Mariana vents rely entirely on pure chemical energy synthesis. This represents a completely independent and alien ecosystem energy model. The research vessel Forca recently mapped new sections of trench. They utilized high-resolution multibeam sonar to locate thermal anomalies. This advanced sonar detects the subtle density changes in water. Warm vent fluid rises and physically bends the acoustic waves. Scientists on board identified 3 previously unknown active black smoker fields. These new fields require future visual confirmation by robotic submersibles. Each new discovery expands our understanding of global geothermal activity. The Mariana Trench continues to surprise veteran oceanographers every year. We have meticulously mapped only a fraction of this frontier. The dark waters hold countless secrets waiting for patient explorers. Marine chemist Dr. Sylvia Earle advocates strongly for these depths. She highlights the critical role of the deep carbon cycle. Vent ecosystems process carbon dioxide falling from the ocean surface. They trap carbon within the vast mineral structures over time. Disturbing these sites could release stored carbon back into seawater. This would alter local ocean acidity and harm delicate organisms. The submersible limiting factor also visited the Mariana Trench bottom. Pilot Victor Vescovo observed the desolate plains near active vents. He noted the stark contrast between the plains and chimneys. The chimneys burst with vibrant, writhing biological activity and color. The vast deep ocean plays a vital role in our global climate. Hydrothermal vents contribute significantly to this delicate planetary balance. Heat from the Earth crust warms the surrounding freezing water. This thermal exchange drives deep ocean circulation patterns globally. Warmed fluids rise and mix with colder abyssal currents. These deep currents move massive amounts of thermal energy. Global ocean conveyor belts rely on this geothermal input continuously. Scientists measure this heat flux using specialized thermal sensors. The Mariana Trench vents release immense geothermal energy constantly. This energy travels slowly upward through the dark water column. It takes centuries for deep water to reach the surface. The massive deep trench acts as a natural thermal regulating system. Carbon sequestration also occurs in these extreme oceanic depths. Microbes consume dissolved carbon dioxide directly from the vent fluids. Chemosynthetic bacteria convert this carbon into organic cellular matter. These microorganisms form the base of the deep food web. This process locks carbon away from the atmosphere for millennia. Deep ocean trenches successfully store billions of tons of carbon. Marine geochemist Dr. Susan Humphreys studies this complex deep carbon cycle. Her research quantifies the mineral exchange at active vent sites. Vent chimneys also absorb heavy metals from the surrounding ocean. Sulfides precipitate and trap metallic elements within solid rock structures. Without these vents, ocean chemistry would be drastically different today. The Mariana subduction zone recycles minerals back into the mantle. Tectonic plates drag carbon-rich sediments deep into the Earth's interior. This slow geological cycle takes millions of years to complete. Volcanic activity eventually returns some trapped gases to the atmosphere. The trench maintains a slow, steady rhythm of planetary breathing. Oceanographers monitor these chemical fluxes with autonomous deep water gliders. Instruments record dissolved oxygen levels near the active vent fields. Data reveals a complex interaction between deep biology and geology. The deepest waters hold valuable secrets to our past climate. Researchers extract core samples from the surrounding hard mineral deposits. These rocky archives record thousands of years of oceanic shifts. Understanding this ancient history helps predict future global climate changes. The deep sea buffers the harsh impacts of global warming. Freezing cold abyssal waters absorb excess heat from the upper atmosphere. This thermal absorption protects surface ecosystems from dangerously rapid changes. However, the capacity of the deep ocean is not infinite. Scientists worry about slowly rising temperatures in the abyssal zones. Changes in circulation could disrupt the delicate vent larval dispersal. The Mariana Trench remains a crucial baseline for climate studies. Its extreme depth isolates it from immediate surface weather patterns. Yet, it remains deeply connected to the global climate system. Dr. Richard Lutz documented the early stages of vent colonization. His important work links vent ecology to broader ocean health. The Mariana Back-Arc Basin contains entirely unique hydrothermal ecosystems. These remote habitats process methane released from the cracked seafloor. Methanotrophic bacteria consume this potent greenhouse gas with high efficiency. They prevent harmful methane bubbles from reaching the ocean surface. This biological filter protects our atmosphere from sudden warming events. The dark trench operates as a silent guardian of our climate. Every hydrothermal chimney contributes to this massive planetary life support. The interconnected nature of Earth systems becomes undeniably clear here. Future research in the Mariana Trench promises truly remarkable discoveries. Many scientific questions about the deep ocean remain entirely unanswered. The evolutionary pathways of extremophiles require much further genetic study. New technologies will soon illuminate these dark, mysterious abyssal plains. Engineers are developing next-generation autonomous underwater vehicles for deep exploration. These advanced drones will navigate the incredibly complex trench topography. Artificial intelligence will guide them through highly dangerous hydrothermal fields. Advanced acoustic sensors will map the seafloor with millimeter precision. Future acoustic imaging will reveal individual vent chimneys in detail. The upcoming Hydrothermal exploration program plans multiple daring trench descents. Scientists will deploy the advanced new submersible named Deep Challenger. This vessel can withstand pressures exceeding 1,000 heavy atmospheres. Its thick titanium sphere protects researchers at 11 kilometers deep. Planned expeditions will target the remote Serena Deep at 10,714 meters. Researchers strongly hope to find completely undiscovered vent fields there. Dr. Alan Jameson currently leads the dedicated biological sampling team. His primary focus lies on the genetic adaptations of extremophile amphipods. Innovations in environmental DNA sampling will revolutionize deep-sea biology. Water samples alone can reveal the hidden presence of species. Scientists will sequence genetic material directly on the dark seafloor. Future scientific probes will measure fluid temperatures up to 400 degrees. Specialized ceramics carefully protect the delicate internal electronic computer components. Researchers also plan to study the mysterious subseafloor deep biosphere. Powerful mechanical drills will penetrate the rocky crust beneath vents. Understanding this subterranean life might explain the origins of biology. Astrobiologists actively study these microbes to prepare for space missions. The icy moons of Jupiter and Saturn harbor hidden subsurface oceans. Europa and Enceladus likely possess very similar hydrothermal vent systems. The Mariana Trench serves as a perfect analog for alien worlds. Instruments designed for outer space will be tested in the trench. The Orpheus autonomous vehicle is currently undergoing rigorous deep trials. It uses visual terrain relative navigation to avoid dangerous obstacles. This exact same technology will eventually guide probes on Europa. Long-term scientific monitoring stations will be established near the vents. Cabled deep observatories will stream continuous ocean data to the surface. Thick fiber optic lines will carry high-definition video to modern laboratories. Established in 2009, this massive reserve covers thousands of square miles. It legally safeguards the volcanic surface islands and the underlying trench. However, many active hydrothermal vents still lie outside these protected boundaries. Dr. Sylvia Earle passionately champions the creation of deep ocean sanctuaries. She affectionately calls these highly vital protected marine areas hope spots. Preserving the vast abyssal plains ensures the ongoing health of our planet. It is a complex, living tapestry of incredible geological and biological wonders. We must always approach the deep ocean with profound, quiet respect. Humanity relies heavily on the unseen ecological services provided by the abyss. The massive trench regulates our global climate and processes our atmospheric carbon. It safely holds the ancient geological history of our world in its sediments. We are gently invited to appreciate this hidden, silent, majestic underwater realm. Imagine the quiet, undisturbed majesty of the vast deep ocean floor. Picture the gentle, rhythmic sway of pale ghost anemones in the current. Visualize the shimmering, distorted thermal heat rising from a black smoker chimney. Think about the slow, incredibly graceful movements of the pale ghostly snailfish. These bizarre, beautiful creatures live their entire lives completely hidden from the sun. They instinctively follow the ancient, steady rhythms of the Earth's internal heat. The deep ocean depths offer a profoundly deep sense of calming peace. The immense crushing pressure creates an atmosphere of absolute, unbroken stillness. Time truly seems to slow down completely in the dark Mariana Trench. Centuries quietly pass with only minor subtle changes to the rocky landscape. The deep sea remains entirely untouched by the noisy chaos of the surface. It is a permanent sanctuary of thick darkness and incredibly quiet endurance. As you slowly drift towards sleep, let your tired mind sink downward. Leave the bright, incredibly noisy surface world far above you right now. Descend peacefully through the twilight zone into the calm, dark midnight waters. Feel the gentle, soothing embrace of the deep, incredibly cool ocean currents. The profound mysteries of the Mariana Trench will safely remain down here. They will wait incredibly patiently in the dark for future human explorers. The active hydrothermal vents will continue their silent, incredibly steady thermal eruptions. The Earth will constantly keep warming the freezing waters of the abyss. Life will beautifully persist in the deepest, darkest corners of our planet. You have safely journeyed to the very bottom of the entire world. Now it is finally time to comfortably rest your very weary mind. Let the slow, gentle currents of the deep completely wash away your thoughts. Allow the peaceful, heavy darkness of the trench to deeply soothe your eyes. The deep ocean forever holds you in its vast, incredibly peaceful expanse. Thank you for watching this relaxing journey into the deep ocean today. I wish you a very peaceful night and incredibly sweet, restful dreams.